Hello and welcome everybody. I'm Cornelis Valk, CTO at EO, an Earth observation company in the Netherlands. I will tell you something about how we use AI for large-scale EO-based monitoring. Our company has as chief business and goal the monitoring of the Earth's surface, providing accurate and timely information on relevant changes. We face a number of challenges in the pursuit of this goal, some of which I will touch upon in this presentation. Firstly, we have a large number of customers, each interested in information on their specific objects at a certain spatial and temporal scale. All those customers have high quality standards. They're used to the quality obtained with human image interpretation. We use a range of data sources to arrive to information on change. And finally, there's an increasing demand for transparency in the methods, controlled AI, and explainable outcomes. I will not go into detail on all these challenges now. We will skim the surface and limit ourselves to remote sensing data. We took a pragmatic approach to the challenge with a framework or system we call Signal Eyes. The way we set it up allows for improved transparency compared to an individual neural network. It also allows for the ability to integrate with expert knowledge. It gives some controllability on what information is and is not used by the models. It has modularity, so we can incrementally expand with better models. And finally, it delivers stable high quality of the changed information. There are a few simple concepts or assumptions, if you like, that we build on. Firstly, an image is a static representation of a dynamic environment acquired by an entity we call observer. Secondly, the content of such an image shows spatially bounded entities that are present on and above the Earth's surface and describes their state at the moment of acquisition. Finally, these spatial entities or objects are part of an observer-dependent hierarchy. More practically, we distinguish object types that are visible on images and categorize them along a few axes and with a few traits. We stick to a high level. Certain objects are in fact kept as properties of higher level objects. Solar panels are properties of buildings. The main classes we distinguish are organized in 3 vertical levels related to position relative to the observer, the satellite. So simply put, height above ground. We separate airborne, elevated and surface classes. To give an example, when looking for information on roads, we want to assure we can trust our findings by excluding areas with thick cloud cover or cloud shadows. These level 2 results are then used together with the original image for objects at level 1. Every individual block represents a dedicated model. This can be a neural network for semantic segmentation, a simple rule, or a more classical random forest. They all share one trait. They produce probability maps. Each pixel has a score between 0 and 1, representing the likelihood of belonging to a certain class. The arrows do not necessarily indicate input to a machine learning algorithm, but can also be applied to correct outputs using simple rules. The sequence is finally used to generate a detection narrative detailing the conditions that were met. To go from probability maps for classes to change maps, we often apply recurrent neural networks. Of course, we also relate this to the customer objects, but I stop here. The system comes with a number of benefits that fit the challenges. It is a modular system where modules can be improved individually without needing to recalibrate downstream modules. Modules are trained separately, so no need to have training data for all classes at once, no need to define all the classes beforehand. Also, certain biases can be reduced by this diversification. Quality is controlled at module level. Upstream improvements automatically result in downstream improvements without any negative side effects. Connections between modules are designed and controlled by humans. They are also used to identify the most probable reasons for the detected change. Finally, we see some stable gains in the achieved quality, especially in more extreme conditions. Thank you for listening. I would love to hear your critical thoughts and experiences. Do you see the benefit of stacking models as is done in Signal Eyes? Or are we just tormenting ourselves and complicating things, while the model that does it all is around the corner?